So next, we're going to define instantaneous velocity. And if the position over time is given by the function p of t, then instantaneous velocity as a function of time is the time derivative of the position. And by the way, in mechanics, time derivatives are common enough that people give this a shorthand. So if you ever see something with a dot over it like this, that means take a time derivative of it. That dot always means time. You know, when you show a prime on something, that means the derivative with respect to whatever the independent variable is. A dot is always time. The units of velocity are length over time. And so that means that in SI units, it's meters per second. Okay, like miles per hour is what we're most used to thinking of, but in SI units, meters per second. And here's some things to recognize, to notice about the instantaneous velocity. First, the absolute value or the magnitude of the instantaneous velocity is the instantaneous speed. So if the velocity is negative 48 meters per second, it means it's moving at a speed of 48 meters per second. And just like with all the directional quantities that we deal with, the sign tells you the direction. In this case, the sign tells you the direction that the thing is moving at that instant. And again, just like, displacement, that sign is equivalent to an arrow in the object's world. Okay, so if we choose this to be the positive direction, okay, and then at an instant, an object has a velocity of negative 30 meters per second, that means at that instant it's moving with a speed of 30 meters per second. That's what its speedometer would say. And since it's negative, I said it's negative, right? Since it's negative, it's moving opposite what we chose is the positive direction, so it's going this way. Okay. And the last thing is, since we talked about position versus time graphs before, on a position versus time graph, V is the slope of the tangent at that chosen instant. So let's think of an example. So if an object moves according to a position function of, let's say this is like 2 times t minus 3 squared. Okay. And let's say this is given in meters. Let's first sketch the position versus time graph. Based on that sketch, let's figure out when the object is moving in the negative direction, the positive direction, and when it's stopped. So when's it moving in the negative direction, the positive direction, and when is it at rest? Okay, and then we'll figure out what direction is the object moving at the instant t equals 2 seconds. And actually, yeah, might as well just calculate the velocity at that instant. Okay, so to sketch this graph, the position is going to be 0 when time is equal to 3. So 1, 2, 3, 4, 5, 6. Okay, so that's the position there. At time equals 0, what's the position going to be? 18. So let's say this is 10, this is 20. So it's going to be you know, somewhere here. At time equals 6, what's the position going to be? Also 18. And it's a parabola, so it's going to look something like this. Okay, so these times they're 0 time, 1 second, 2, 3, 4, 5, 6. And by the way, there's no mathematical reason, obviously, like you've always dealt with functions that have negative values. There's no problem with a function having negative independent variable values. In physics, we just don't use negative times. There's no reason that's true, but nobody does, so we're not going to do it either. Okay, so we're going to imagine that time equals 0 is when this motion starts, or when our interest in this motion starts. So what's the time interval where this object is moving in the negative direction? Yeah, 0 to 3, because if you think of the slopes of the tangent lines of all these points, those slopes are all negative. Okay. They're getting closer to 0 as you go. So this object is moving in the negative direction on the interval from 0 to 3. Is there any place where this object has 0 velocity? Yep, at t equals 3. So that's where it's at rest instantaneously. It has 0 velocity. And then when is it moving in the positive direction? Yeah, as far as we go. Yep, exactly. So 3 to infinity, or 3 to 6, the way I drew it. Based on this graph, where are the places where the speed is the greatest?
At the start, or it gets infinitely faster.
So this is 0 slope. The absolute value of the slope is speed. And so the biggest absolute value of the slope is as you get closer to 0 and as you get closer to 6, right? And it slows down as you get closer to being at rest, and then it speeds up again as you go away. And then, so let's calculate for part C, the velocity at time equals 2 seconds. So to do that, we're going to go back to the function. Where's this? Okay, so our position function is 2 times the quantity t minus 3 squared. To calculate the velocity as a function of time, that's the time derivative of the position as a function of time. And so that's equal to 4 times the quantity t minus 3. And then the chain rule says you have to take the time derivative of the stuff inside the parentheses, which is just 1 in this case. So we get 4 times the quantity t minus 3. So now the velocity then, if you want to find it at a specific instant, now that we have the function, you can just plug it in. So the velocity at 2 seconds is 4 times the quantity 2 minus 3. So, yep, negative 4 meters per second. And the negative means it's moving in the negative direction at that instant.